the score. Uh, uh, so what I was interested in showing you was, let's say you want to score the dose. So how you define your phantom. So basically what they have done, let's analyze this input file. So they have defined a world volume that has a half length along XYZ direction in 2 meters. And then they have defined a water phantom that is air phantom. It is made up of air, and it is a child to the world volume. It's that means is inside the world volume, and it has a half length of like along XYZ of 10 dimensions of 30 centimeter and dimension of half length of 10 centimeters. And from like whenever you place any object in the world volume, it automatically is set to the center of the world volume. So not necessarily you want to place your geometry at the center of the world. So you might be interested in translating or rotating them, like in this case, geometry case. Uh, all of these geometries are not at the center of the world volume. I have translated the shielding volume and this source box and this water phantom by different amount along along the z-axis. So here also they are doing the same. They have translated along the z-axis by minus 30 centimeter and give the color blue to the phantom. Then the quantity they are scoring is those to the medium. Where they are scoring it, they are scoring in water phantom, not in the whole world. And do they want the output on the console? That means the running window. So yes, they are writing. And what to do with the if the output file already exists? So just overwrite it, or maybe just you or don't want to uh, um, you don't want to uh, lose the file that is already created. Then there is another option that you can use, is like you can just add keep adding one to the output. I can show you what I mean by that. Where is the So in our case I have used this approach of not losing our output. So here is our scorer. Yeah, so um, yeah, if the output file already exists, just increment it by one. So we will never lose our output, no matter if we get like 10 outputs, so it will start counting from 0, 1, 2, 3, 4, and this way you will have all the outputs of all the runs you make, and you will not lose any output that you of any run you make. So I prefer to use increment because sometimes I want to analyze what is the problem and what happened. So it is useful. Otherwise, if you don't want to check it, you just can use it like if already exists and just override. Here is the viewer that they have defined, like we already discussed. Let's make it view. Yeah, I have to open in text file. And then here is the physics module, and here is the source definition. They have defined a proton beam with the beam type. Uh, source type is the beam, and they have defined the particle as proton beam and energy, and the and the distribution type is Gaussian and elliptical. So now I think you are able to completely analyze any input file of Topaz or the example files provided in Topaz, because you know about the source definition, the physics list, They have used it's not modular. They are just using one simple module. So yeah, it can you can call it it's gent for modular physics list they are using. Yeah. So here they compute the dose. We can check it. Let's check it. I open it in. I need to turn on. I want to turn on this viewer to true, and then Control C, CD. And then this. That's it. You see, it's the world box. This is probably the water phantom and or not sure. Yeah,
Yeah,
we are
that's the
not
water
seeing the
phantom.
world volume. Yeah, they are like made
Mm,
the world as invisible. So what we are
yes.
looking at is the water phantom.
Mm,
And if we want to run it, you see the proton beam is crossing from the center of the water box.
yeah.
And I guess it is how many particles did they run? They run 10,000 histories. So yeah, we can wait and yes. So they finished. Oh, so
Okay, it's done.
no, it's actually 100,000. So let's reduce it a little bit less. We are not
Okay.
interested in simulating this much. I think 10,000 is good enough to see what's actually happening and how the score works. Okay, uh, I guess simulation has finished. And you see, it has scored
Yeah,
dose in medium and it has provided you with a single value. So
yeah.
maybe you are not interested in just calculating the sum of the dose deposited. So here is the value, but maybe you want to know the standard deviation and other things about the dose deposited.
Mm,
You can do that as well, like I shared before, or we
yeah,
I mentioned discussed before. There are
yeah.
different
Like the
things you
mean
can,
and the
yes, standard.
sum and the standard deviation. Yeah.
Yeah, yeah.
Mm,
So and let's look at another example now, like dose in medium versus the. Let's check which one maybe. Okay, those in voxel materials. So we have here our world volume, that is XYZ half length of 2 meter, then a water phantom, yes, water phantom made up of water, parent is world, and XYZ dimensions of half length 30 centimeter translated by 30
let's
centimeter
see.
along Z axis, color is
Color is
blue,
blue.
and the phantom is divided into bins of equal
Yes.
size, that is like along 10 along x-axis there are like 10 voxels, y there are 10 voxel, and z there are 10 voxels, and then they have like specified specific material to each of these voxels. So let's check this as well. Voxel material, it should be
Mm,
here, yeah.
yeah.
So here like they have defined since it is like 10 by 10 by 10, so it's 1000. So they have
Mm.
specified the top layer as water, then there is air everywhere, then there is water, then there
It's
is
lead.
lead, and then there is water. So you
Okay.
can also use this kind of setup. So let's first check the complete check of this. Okay, so and then they have rotated the phantom along y-axis by
Why?
290 degrees. We'll check it. And then they are
270.
yes, 270.
Mm.
degrees, and they are computing those to the medium in the component phantom, and they are outputting their output on the console. And if there is any output file present, they directly overwrite it. And
Mm.
the viewer type is OpenGL, and this is just the viewer settings. This is physics list, and here also they are using beam source using Proton. So yeah, and let's try to run this example. What's the name? Those in voxel.
Mm.
Voxel. Okay. So you see they have divided their water phantom into uh, they have voxelized their water phantom and gave each component a different medium or different material is assigned to it. And
Mm.
yeah, we can count like voxels. It's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So yeah, they have
Mm.
it's like 10 by 10 by 10.
By 10, yeah,
Yes,
1,000.
so and if we run the simulation, oh, just wait, how many particle are they simulating? Yeah, so it's
100.
100, so it's
Mm.
not a problem. But like my computer is stuck because when you use a material that is like or a phantom that has like too much too
Ma-
how to say mediums or
Too many
complexity.
material.
Yeah, no, particularly the complexity, your viewer
Okay.
needs a lot of RAM, and maybe your computer is not strong enough to handle that, and it may cause problems for your visualization or the graphical user interface checking. Like here,
Okay.
in my case, it's stuck, so we can go without uh, like viewer. I can turn off the viewer and then we can directly run the simulation. Yeah, so you see, it has calculated those in each and every voxel.
Yeah.
Somewhere the dose deposited is 0 and somewhere there is some value. But the problem comes at it is yeah, they have stored the dose in this file. So
Okay.
let's check this dose at phantom.csv.
Phantom. Yes.
Dose at phantom. Yeah,
Is that it? Mm.
and you see it is a Excel file. Well, yeah, like I said, it's
Okay.
an Excel file. You can just, if you want to draw a plot, you can just copy paste this and you can extract whatever information you are interested in.
Okay.
But from voxel getting voxelite phantom getting PDD or any kind of this things may be difficult. That's why I prefer to use DICOM output settings. So we'll check it next week for our own simulation setup, and then for last 2 hours we will spend on analyzing using NumPy or Python. Okay.
Okay.
Okay, then let's check one more example now. Uh, we have checked the dose. Let's check the dose volume histogram. So here they scored dose volume histogram, cumulative dose volume histogram. They have like they define the world volume. Then there is a phantom that is made up of lead, and it is translated along z-axis by 30 centimeters minus 30 centimeter. They have voxelized the phantom into uh, 10 voxels in each in direction of x-axis, y-axis, and z-axis. They are computing those to the medium, and they are reporting the sum dose deposited in gray and the cumulative dose volume histogram. And histogram bins, there are 100 bins in your histogram, and the minimum is 0, and the max dose deposit is 0.0001 gray. And then is like it's the viewer, and then it's the same beam source that they are using to show the example, and the histories they are running is 100. So yeah, we can check this. Exact. There's one on Instagram. You see, this is outer is the world volume, and here is your voxelized phantom in blue. And
Yes.
if you run the simulations, it is running. Uh, you see it, the run finished with the 100 particles. And this blue one is the proton, and this green one are the electrons or photons, I guess. Yeah, photons. And this red one is the electron. And since it is because our phantom is made up of lead, I guess. So that's why it's not passing through. Yeah, it's lead. And you see, it provides those deposited in each 100 bins of the dose volume histogram. It ends at 99 and starts at 0, 0, 0. And there are like over voxels. Yeah. And here is the dose deposited in your phantom, and it tells you which file you should check for to get check for the dose volume histogram. It's dose at phantom volume hist, and this is the output in the energy or dose deposited inside your water phantom. So it's dose at phantom.csv. So yeah, so this way you can